Having set up the general linear algebra we're going to use for our quantum mechanics, now we can look at some consequences in quantum mechanics that we can understand from that mathematics. As we said, a postulate of quantum mechanics is that all measurable quantities can be associated with a Hermitian operator. For example, energy, the Hamiltonian operator, and momentum. Other measurable quantities, including position, angular momentum, and spin angular momentum, for example, also have to have operators. We should note as an aside here that some operators that are useful in quantum mechanics are not Hermitian. For example, non-Hermitian creation and annihilation operators that are used extensively in quantum optics. Though these non-Hermitian operators are mathematically very useful, they do not represent physically measurable quantities, so they do not have to be Hermitian. We will have to postpone any discussion of these operators for some later time, however. Now we're going to look at some of the important properties of these Hermitian operators that are associated with measurable quantities. In particular, we will be looking in general at what we can say about eigenvalues and eigenvectors of these Hermitian operators and about the eigenvectors of different Hermitian operators. How do we know if two operators can have the same eigenvectors? This in turn is related more generally to the idea of uncertainty principles. We will start by looking at what happens when two Hermitian operators commute or don't commute. This has some very important and quite physical consequences.
In general, in quantum mechanics, we're going to be working, of course, a lot with Hermitian operators because they represent observables, observable quantities in quantum mechanics. And if we have two Hermitian operators, A and B, representing possibly different physical observables or different physical variables, it's very important to know if these operators commute. That is A after B the same thing as B after A? Remember that because these linear operators obey the same algebra as matrices, and indeed we can essentially always choose to write them as matrices, then in general this is not true. It's not in general true that for two operators or two matrices that A after B is the same thing as B after A. It can be true, but it's not always true. For quantum mechanics, it's useful algebraically to define an entity, this entity here, which is A after B minus B after A. And we call this entity, with these square brackets here, the commutator. An equivalent statement, therefore, to saying that A after B is equal to B after A is to say that the commutator is 0. Now, strictly here, A and B are operators, and the 0 on the right, if we wanted to be strict about it, is actually a number, so this isn't mathematically quite correct. But we could, if we wanted, add an identity operator on the right to make it a mathematically correct statement. However, mostly for historical reasons, because we started out using differential operators in here, we don't typically bother to write the identity operator explicitly here. So if it looks like we're writing operator on the left equals number on the right, we will usually find that it's all right just to put in an identity operator there if we want to keep this mathematically correct. But usually, we don't bother to write this identity operator. So it will usually be obvious from context whether there should be an identity operator in there or not. But mostly in the algebra with commutators, we are not at all careful to make sure that what we have on the right here is written as an operator, even though it has to be an operator in a statement like this. Now, if the operators do not commute with one another, that means this is not true. This would be the case if the operators do commute with one another. And in general, then, we can choose to write that whatever they do equal on the right is some operator. And by convention, for no particularly strong reason, we tend to write whatever the operator on the right is here, we write it as I times C, where C is some operator. So if the commutator of A and B is not equal to 0, we have to say it's equal to something, and we'll say that it's equal to I times C. And we sometimes refer to this operator, C, as the remainder of commutation, or what we could call the commutation rest. Now we're going to look at two important statements about commuting operators and sets of eigenfunctions. So our two statements are: operators that commute share the same set of eigenfunctions, and operators that share the same set of eigenfunctions commute. So these are not the same statement. They're two quite different statements, but they're both true in the case of commuting operators. And we're going to prove both of these statements. Technically, we're only going to prove them for the case of non-degenerate eigenfunctions and eigenvalues, although we can in fact complete the proof even for the case where we have degenerate eigenfunctions and eigenvalues, that is, multiple eigenfunctions for the same eigenvalue, but we won't go through that minor complication in the algebra here. So let's look at this proof. Suppose that operators A and B do commute, and suppose that the psi n here are the eigenfunctions of the operator A, and those correspond to eigenvalues ai. Then, because these operators commute, A after B operating on psi should be the same thing as B after A operating on this same psi, this psi I here. And of course we know what A operating on psi I gives us. By definition, because the ai are the eigenvalues of the operator A, then A operating on psi I gives us ai times psi I. And of course, this is just a number here, so we can move it around. It commutes with everything. So that means this is all equal to the number ai times the operator acting on psi I. So that means that A after B operating on psi I is ai times B operating on psi I. And I put these inside these brackets here. These are not commutator brackets, they're just brackets, to emphasize that this object in here is just a vector. So we have A operating on a vector is giving us ai times that vector. But that means that this vector must be the eigenvector psi I, or be proportional to it, because we have A operating on this vector gives us ai times this same vector. And since by assumption here we're presuming non-degenerate eigenvalues, then this vector here must be psi I, or be proportional to it. That is, for some possibly quite different number bi, B operating on psi I must give us some number times psi I. Because as we said, this vector here must really be just psi I within some constant or other. This kind of relation, of course, that B operating on psi I gives us a number bi times psi I, holds for all of these eigenfunctions here. We didn't care which of the eigenfunctions we chose for this particular proof so far. So these eigenfunctions are also the eigenfunctions of the operator B, because this is just an eigenequation. And this has to hold for all of these eigenfunctions here. We just proved that. In this case, the eigenvalues are these numbers bi. Hence, we've proved our first statement that operators that commute share the same set of eigenfunctions. Note that in general, these numbers ai and bi are not the same numbers. They could conceivably be, but they are not necessarily the same numbers. But the eigenvectors have to be the same eigenvectors. Now consider the statement, operators that share the same set of eigenfunctions commute. Suppose that our Hermitian operators, A and B here, share the same complete set, psi n, of eigenfunctions. And they will have associated eigenvalues an for the case of the A operator and bn for the case of the B operator. Then A after B operating on psi I will be A operating on bi times psi I, because this is the eigenvalue we get, bi, by operating with b on psi I. Well, we can move this number around if we want. We don't really need to. A operating on this vector here, which is just some vector proportional to this eigenvector psi I, also of the operator A, just gives us another factor ai out in front here. So A after B operating in psi I is ai times bi times psi I. And similarly, we can do this argument the other way around. B after A operating in psi I is the same thing as B operating on the number ai times psi I. Of course, it doesn't matter what order we put the numbers in. And B operating on some number times psi I, because psi I is an eigenvector of B, just gives us bi times that same vector. Hence, for any function f, which we can expand therefore in this complete set of eigenfunctions psi n, so here's our expansion with expansion coefficient ci. For that function, we have that A after B operating on f is the sum over all the ci's of A after B operating on psi I. So we know that's just ai times bi times psi I. And similarly, that's just the same thing as bi times ai times psi I everywhere in this sum here, because numbers commute. And we know that that's the result of B after A operating on f. We could similarly check that out. Since we've proved this for an arbitrary function, that A after B operating on f is equal to B after A operating on f, then we've proved that the operators commute. Hence, we've proved our statement that operators that share the same set of eigenfunctions commute.
So now we have proved our two statements. Operators that commute share the same set of eigenfunctions, and operators that share the same set of eigenfunctions commute. This equivalence has an important quantum mechanical consequence. Suppose the commuting operators represent different measurable quantities. An example of such a situation is the case of a free particle, that is, one for which the potential is constant everywhere. In this case, the energy operator, that is the Hamiltonian, and the momentum operator have the same eigenfunctions, that's plane waves. And the operators for energy and for momentum commute with one another. In this case, if the particle is in an energy eigenstate, then it's also in a momentum eigenstate. And the particle in this case can simultaneously have both a well-defined energy and a well-defined momentum. We can measure both of these quantities and get perfectly well-defined values for both. But what happens when the operators do not commute? We will look at this in the next section, and it has profound consequences in quantum mechanics.